Okay, so we finally gotten through a lot of the slower, I don't know if I would say boring parts of our coursework, and now we're at where the metal really starts to hit the meat with electricity. Now, electricity's come a long way in the past 100 years. Early on, I mean, you can even see this in our A.I.K and in the Cessna 120 that's out on the hangar floor. Everything is super simple. It's all analog. Either battery or some sort of generator is producing power, and it all just goes to the lights. A lot of the instrumentation's not electric; it's all suction driven or vacuum driven rather. And so now, if you look at like 777X, 787, they have circuit breakers that are all digital. Now, that's a huge jump. And you as an A.M.P., you're going to be expected to be able to troubleshoot any and all of it. So that could be as simple as changing a light bulb, or it could be as complex as trying to troubleshoot a slight voltage drop on the maintenance pages on a 777. You need to be able to be flexible to work on the real complicated stuff, and then also be able to downgrade your skill set to be able to go back and work on the little things. Now, to really kind of hammer that home, I want to tell you a pilot story. Whenever I was a kid, I was hanging out just right over here at the flying club whenever it was like a really big deal. And my flight instructor had a friend come in who is a 747 pilot. Now, your brain is thinking like, this guy's the best in the business, and he's probably the most highest paid pilot I think probably I'd ever been face to face with. And like regular jumps from America to Europe and Africa and back and forth and stuff. There's no telling how much money that man was making, especially even back then, whenever the pilot pay wasn't what it is now. And so he got in my little Cherokee 140, or it wasn't mine, it was the club's Cherokee 140, and he took off. And whenever he came back around to land it, he bounced it. He bounced it bad, to the point where it was like almost kind of scary, where he came up and then boom, 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 and just skipped down the runway. And the thing is that like, even though he was a 747 pilot and like he had all these hours and stuff, he had atrophied in some of the basics, like just simply flying the airplane. He'd gotten so used to like crew resource management and just managing the flight deck and flying what was essentially the big computer, that he had lost a lot of his just finesse for being able to just fly the plane. But the thing is that like at some point, like if all the systems that help you on a 747 just like went away, all those basic skills are the only thing that's going to save you and put the plane back on the ground. It's no different for us as A&P mechanics. We can be really good at troubleshooting computers and the digital stuff, but at the end of the day, it's electrical current that goes into some sort of motor that causes something to happen. And that's really what matters. And so pay attention to this next little bit, because this is where you're going to build your foundation. Watch this video multiple times. Ask a lot of questions when you get here to the hangar, or we're going to put you through iteration after iteration of troubleshooting the really basic stuff and the really difficult stuff, and then teach you how to teach yourself. Because the thing is that this progression is not going to stop anytime soon. It's just going to keep on going. So the people that are successful are not the people that are just like wizards at the thing. They're the people who can continually learn and teach themselves, who can get in the manual, who can read, who can download and digest, go find things other places, go read the art of electronics and understand like what a MOSFET is and all these little nuances that make a really good technician a really good technician. Like typically aviation is kind of like chopped down into different like fields, avionics being one of them. But as time progresses on, you're starting to see avionics start to take over things. Like the 787 doesn't have hydraulic brakes like a typical thing. It's all electric. So that means that it really kind of falls into like the avionics world. It's like, okay, well, like if you're going to troubleshoot the brakes, then you have to go get the guys who are really good with electricity. And that situation is going to keep on happening. We saw it happen with flight controls. It used to be all cable flight controls. And if you're working on 737, it still has cables. But like everything else is all fly-by-wire. It's avionics. You're doing flight control rigging. It's avionics. So like this is a subset of aviation that's going to continually grow, and you need to be really, really good at it if you want to be successful. Okay, so something you're going to hear me say a lot is be brilliant in the basics. So if we want to be brilliant in the basics, where do we need to start? We need to start with the basics, with the fundamental level of what electricity is. And to understand that, you need to understand atoms. So let's talk about atoms. So an atom has three separate parts, all right? So here we got our atom. All right. Inside there, we have two fundamental particles. We have a proton, which is positively charged. We have a neutron, which has no charge. It's neutral. All right. On the outside, use purple yet, of the nucleus, and this is what this is called, the nucleus in the middle, we have an electron, which is negatively charged, which orbits the nucleus. So that's an atom. The atoms have different energy shells, or these different kind of orbits of electrons. So a hydrogen atom, which has just one electron, has one energy shell, and that's it. But other more complicated atoms have multiple energy shells with multiple electrons. And then you could have another shell around with another set of electrons orbiting it. Now these different shells will fill up with free-floating electrons, these valence electrons that go from point A to point B. All right. So as electrons encounter the atom, it can grab them and hold on to them, or it can pass them back off. Now, as this exchange of electrons happen, that's how we get current flow. That's what defines a lot of the chemical properties of an atom, like how many electrons can it hold, how tightly does it hold on to them, or how freely does it pass them off. So good conductors are ones that just give freely of their electrons. They grab them and they pass them off. They grab them and they pass them off. Bad conductors are the ones that grab them and they hold them and they don't pass them off. So you think like wood and copper, or the two different, I guess like wood's not a base element, but the substances that make wood up, like say carbon, they grab and hold onto their valence electrons. Whereas copper is a fundamental element. Aluminum is another conductor we use on the aircraft. Gold, a lot of spacecraft. They freely like dish off electrons on a regular basis and cause a current to flow. So let's kind of like draw out an idea of like what that actually looks like. So you have an atom, and you have another atom. Now every one of these atoms has an orbit. All right, different energy shells, and they have electrons that are in that energy cell. And let's say that this in particular atom can take up to say 2 electrons in its lowest level shell, which is true. They all can do that. All right, so you have a free floating electron that's just floating out there in the wind, and it stumbles upon this atom. Well, this atom can take 2, so it grabs him and puts him in orbit. But as he's orbiting and going around, he encounters this other atom right here. Well, that electron hops over to this guy's shell. And then he goes on until something encounters it, and then that electron just goes on like that. That's how current works. You push an electron to one atom, it grabs it, holds onto it, passes it off to the next. Just like a little game. They're just passing off one way or the other. Now I can remember a Star Trek movie where Spock was talking about like, well, this is just ionized gas. And I always wondered like, well, what is ionized gas? And all it is this process. Now, as the atom has a proton in the center, and the neutron, which is neutral, and then one electron going around, it's neutral. It's like you have a positive and a negative that cancel each other out. But if you pick up another electron on the outside, well, now you have one more negative electron, which means that it becomes a negative ion. All right. Now, different elements have different configurations, so it's not true of every single atom. But essentially, like the more electrons it picks up, the more those energy shells fill up, the more negatively charged that they become, depending on how many protons are in the nucleus. All right, so we've talked about why electrons flow, and we talk about like what they flow in and how do we control that flow. Let's talk about the two different types of electron movement that could potentially happen. One you should be familiar with is called static. Now, like we've all kind of shuffled across the floor and touched the doorknob and shocked each other. I love to do it. If I have wool socks on, I'll do it across my living room floor and then go touch my wife and try to shock her. It's like a fun little game. That's static electricity, all right? Static electricity is going to matter a lot to us, and it's going to matter even more and more and more as time goes on. Static electricity shows up in like lightning. So like as the aircraft flies through the clouds, the air, and all the good stuff, it's picking up free floating electrons. It's just all those shells are starting to fill up, and they have to go somewhere at some point. So we have to have some way to dissipate that. If not, you'll end up causing either a lightning strike, or somebody will walk up and touch the plane whenever it lands, and it'll blow them back because it's picked up so much free floating electrons that are out there. So if you'll notice on the wings, you'll have static wicks. Those wicks have like little rods that have like a fabric that comes at the very end of it that helps dispel those free floating electrons. It just opens them up, and as the plane flies along, it helps just like discharge them. So that way we don't have that electrostatic discharge to worry about when we touch the airplane. Whenever we fuel an aircraft, we're going to take a grounding wire. We're going to ground it to the earth, and that what happens is that you have like your plane, and it has all these like free floating electrons in it. Well, we have to get rid of those somehow, and so you have the earth down here, so we connect it and then we create a pathway for them to flow, because the free floating electrons want to go to where there's like a vacuum of electrical potential, that there's not as many electrons down here, so that there's a lot of like open shells in those atoms. And so the electrons that are full up and they're getting all super tight because they don't like being close together. If they're all tightened up in their own atoms, they want to go somewhere and they see like a path. Imagine if you had like a stadium like packed full of people. You're coming out of a concert or whatever else, and you're just like, oh, I just want to get away from all these people. I just want to get to my car and go home or whatever. And as they come out of the stadium and they go into the parking lot, they start dispersing like crazy. That's what's happening right here. And that's all it is static electricity that's packed up on the airplane that's trying to go. They're trying to leave the concert to go, to go home, to disperse and get away from everybody and take a nap and do the thing. Now, that's static electricity. That's going to come in super important when we start talking about electronics, and we're talking about like electrostatic discharge. And we won't get into that a whole lot just yet, because we want to build a foundation. We want to be brilliant in the basics before we really start to apply what we're learning. But that's static. The other one is dynamic. Now, dynamic electricity is the electricity that we want, that we generate, and we shove down a conductor to go do something. And this is also, whenever it jumps like that goes from being static electricity to dynamic electricity. You'll very rarely ever hear anybody refer to it as that, but that's the technical term for electricity that's generated and pushed down a conductor to a device of some variety. Okay, so here we are at our electrical trainer. We have a battery. Now, we need to talk about another aspect of current called current flow, or conventional flow, or electron flow. Now, conventional flow said that electrons flowed from the positively charged side of whatever to the negatively charged side of a thing. So on a battery, like the positive terminals where the electron starts its journey, goes through the circuit, and then ends up back at the negative side to work its way across the cells and then start all over again. And this is the way it was, or considered, for a long, long time. It started with Benjamin Franklin, and it just went on and on and on like that. Well, then sometime in the past, about 50 years, people started investigating, and they said, it's not how it works at all. It's actually the other way around. That actually the atom starts its journey, or the electron starts its journey on the negative side and goes the other way, rather than to the, and then ends up in the positive. And that became known as the electron flow. Now, electron flow, conventional flow, it really doesn't make a hill beans difference, but the official position of the FAA is that electron flow is standard from negative to positive. So keep that in mind, that whenever you're trying to safe the system, you take the negative side off, not necessarily the positive. Okay, so now let's talk about a little romance, all right? Now, if you think about Han Solo and Princess Leia, they're totally different. Han Solo is this like rogue pilot that doesn't want to work for anybody. He's got no loyalty to anybody, and he just wants to get paid and go home. Princess Leia is the idealist. Like, she's the princess that Darth Vader's got captured up in the Death Star, and she wants to undo the Empire and all this other kind of stuff. Han Solo could care less. All right, the two are totally opposite. But by the end of the movie, they're smooching on each other and having a grand old time, and you have this whole long soap opera between, the first Star Wars, the real Star Wars, and then the next two movies. By the time of Return of the Jedi, they're all loving each other and everything else. And it really kind of comes to the peak in Empire Strikes Back, if you haven't seen the movies. But that teaches us something about electricity right there. You have Han Solo and Princess Leia, complete opposites, yet they attract. All right? But if you have two people that are the same, they generally don't attract. They have a lot of friction. They push up against each other. Same thing is happening with our electrons. If you have a positively charged electron and a negatively charged electron, they get together and they're super duper happy. All right. If you have a bunch of like positively charged electrons, they want to get out. So that's what's happening in our static discharge type situation. That's the concert scenario where there's just too many things on one place that are too similar and they just want to go. They're repelling and they're pushing each other off. So you'll see this, and this becomes very, very important with magnetism, which we're about to talk about, that things that are similar want to push against each other. Things that are different will attract, and they want to get together and have a return or a Empire Strikes Back moment like Han and Leia. Okay, so now that we have kind of a fundamental grasp on electrons and how and why they flow, let's talk about magnetism. Now, magnetism is very, very cool for a lot of different reasons. One of which I personally think is like super cool, is that we don't understand it. We understand how it works and we understand the implications of it, but the ultimate nature of like why is ferrous metals magnetic but other things just aren't? Why are there some that are kind of sort of in the middle but they're not quite 100% like ferrous metals? We don't really fully grasp all the implications of magnetism. However, you use magnetism every single day in one way, shape, form, or fashion. Your doorbell, for example, is usually has a solenoid type device in there. Anytime you start your car, it is using the principles of magnetism. Your phone, as you plugged in your GPS, it has an internal magnet that's reading the Earth's magnetic field and helping you navigate. We've been using magnetism since a couple hundred years now. The first time that somebody took a bowl of water and put a piece of like iron in there to let it float on some sort of medium, and then it aligned with the Earth's magnetic field, all of a sudden, boom, somebody kicked off and said, hey, look, we can steer a boat with this because this thing will always point to one direction. So if that's like always a known direction, then we can kind of start determining where we're going elsewhere. And then from that, it just got extrapolated and extrapolated and extrapolated until now we have an entire methodology on how to navigate via the Earth's magnetic field. If you're getting your private pilot's license, or if you're doing like land navigation, you'll know all about taking a compass and then saying like, this is the azimuth that I'm going to work off of. I have to take these factors into consideration. I don't want to get too close to certain things because it'll throw the compass off and it'll throw my navigation off. All of this basically boils down to a fundamental principle we're called magnetism. So let's dive into that. Okay, so to understand magnetism, let's look at a magnetic bar, all right? So this is going to be our magnet. Now, what's known, what we call the north end of the magnet, our positively charged end. The reason why we call it north is because it was originally used to be the north-seeking end. And so if you're going to navigate with a boat, like you would paint one end of it and you would set it in the water and it would swing around and be like, oh, okay, well, like now I know which end is north or which end is south since we've marked it. And then we would always use that north-seeking end to point to north. And so if I wanted to go west, then I would set it down and I would take a left-hand turn. If I wanted to go east, I would set it down, look at it, and say, okay, well, this is north. I'm going to take a right-hand turn, so on and so forth. So we have a north end of the magnet. North end of the magnet is positively charged and wants to send electrons out from it. So we're going to go like so. All right. Now the opposite end, the south end of the magnet, wants to pull electrons to it. This creates an interesting situation that the north end of the magnet is pushing electrons out. The south end of the magnet is pulling electrons in, and what we get is this weird feedback loop where an electron gets pushed out, then gets grabbed and pulled back in. All right, and this happens on both sides, just like so. All right, now it's happening multiple times. And from that, we get what's called lines of force, all right? So these are lines of force. This also will tell you why like ends will push against each other. They won't necessarily attract. Because you can imagine if you had a south end magnet over here, as these electrons get pushed out, this south end is grabbing them and pulling them forward. But if you said, hey, look, this is the north end of the magnet, and you push an electron out, this one's also trying to push electrons out, they're pushing up against each other and pushing away. Same thing on the south end. Is that like if you put two south ends together, they push away from each other because they're trying to pull electrons in, they're pulling them away from each other, and they don't get along. So this is the basics of how magnets work. Okay, so a couple of things to talk about before we move on into a little bit more complicated implications of magnetism. First off, let's consider the Earth, because this is going to be important when we start talking about navigation. Earth has a North Pole and a South Pole. All right, polar bears, penguins. Our lines of flux do like this, coming out of the Earth, because it has a ferrous core that's all turning around. This is how the Earth's magnetic field operates. This is going to be something that we have to contend with when we start to do compass swings, whenever you start to look at how the different navigation systems start to integrate with each other. It also will have to do with like avionics failures that are closer to the poles, because as the sun's discharge hits the Earth like so, the reason why you have like an aurora is because those particles are coming and hitting the Earth's atmosphere. Well, some of them actually penetrate, and if you're flying in those areas, it can mess with your avionics a little bit. So it's something to be considerate of. Another thing with magnets that's really interesting is that, let's say you have a piece of iron that's magnetized, and it is shaped, say, like that. For whatever reason, the lines of flux really congregate on that point. Any sort of odd shape, they always go, they'll concentrate on those points like that, and they'll be stronger here than it will be, say, like over here. It likes corners for whatever reason. So just, that's something to remember as you go in and you start dealing with magnets. Okay, so let's put our knowledge of magnetism to work. Let's go back to a guy named Hans Christian Ørsted. Yeah, Ørsted. Hans Christian Ørsted realized that he could take a compass, walk up to a wire that has current going through it, and all of a sudden the compass needle deflected and went towards the wire. And he shut the current off, and the compass went back to pointing north like it normally did. He realized that it wasn't the wire itself that was attracting the compass, but it was the current that was going through it. It was producing what we call now an electromagnetic field. That if you have a wire and current is passing through it, then it starts generating its own electromagnetic field, like so. You can experiment with this. You take a compass and point north and go walk under high tension wires, and you'll see that the compass deflects. You can do the same thing with any sort of electrical conductor that has power going through it, and you can watch it mess with compasses. This is something that's really, really important. So whenever we do compass swings, we'll have a compass card, and we'll go through various configurations to see what will mess with the compass. We'll key the radio and see if the compass deflects or not. You'll be on the compass rose out here on the airfield, pointing north, and to have your compass set up and just see what the deflection is on it, based on the configuration of inside of your aircraft. Now, a couple of rules with electromagnetism. Generally speaking, the fields, the electromagnetic field that is produced by the conductor is directly proportional to the amount of current going through it. So it means that if you're at a 1 amp level of current, then you have such lines of force, right? But if you go to 2 amps, so you double it, well, then you double the lines of force, and you keep on doing that, and it gets bigger and bigger and bigger and more powerful as it goes. Also, we're going to kind of get a little ahead. I don't want to get into laws just yet, but there is one rule that applies directly with this. It's called the left-hand rule. So here's my left hand. If I were to grab a wire and point my thumb in the direction the current is flowing, then the lines of flux go that way. They curl over the wire just like so. They also make concentric circles. So let's say like this is our wire. Our lines of flux look like this. So on and so forth. Now this sounds like kind of like theoretical abstract stuff until we start getting into solenoids, generators, all that kind of stuff. All of this will start to become extremely relevant, but you need to understand kind of the basics of electromagnetism. So essentially, the very, very basic approach to this is that we have a wire, current is going through it, and because current is going through it, electromagnetic lines of flux get produced around it, winding this way. If I take our left hand, point in the direction that the current's going, and our fingers will show us which way those lines of flux actually curl. Okay, so now let's talk the basic components of electricity. Now that we understand the kind of the fundamentals of how it works, the basics of how it works, what are the basics of what we're actually looking for inside of a circuit? First is voltage. We're going to go deeper in these here in a minute. We have voltage, then we have current, and then we have resistance. Now, there's some other things that we need to talk about, like capacitance, inductance, stuff like that, but these are the three basic fundamentals of what an electrical circuit is. Voltage is the electromotive force, the amount of electricity that's the potential energy that's there, or the potential electrical force that's there. So if you have a battery, there's a lot that's there, but you look like an airplane that's not powered, there is none there. So we have a lot and nothing, and they want to flow out. Remember the concert, there's like a lot of dudes here, no dudes there, and they all want to go into the airplane. Okay, current is expressed in amps, and that is the rate in which they're going. So if there's a lot head that way, well, there's a lot of current inside of that circuit, and the resistance is expressed in ohms, and that's how much the current is encountering resistance to slowing it down. All right, so let's break down each one of these and examine them in depth, and then we'll start to see how they all play together whenever we get to Ohm's law. Okay, let's start with voltage. Now, we said earlier that there's a potential difference in energy levels, and that causes a certain flow. So let's say you had 2 water tanks. All right. Now this water tank on the left here has a lot of water in it. It's full of water. This guy over here, it's got no water. It's totally dry. And we were to connect it with a pipe. What would happen is the water in this side would flow into this water bucket vessel thing. And so it would go this way like so and start to fill up. And it would fill up and fill up and fill up and fill up, and this one would steadily come down. It would start to decrease because that water is starting to rush over on this side, right? Until eventually you got to where they were at like an equilibrium. They were basically the same, provided that they're level, which my drawing is cockeyed, but provided they were on a level surface, they would eventually just equalize, and you would have 2 water buckets that are at the same level. This is the same concept as voltage. That essentially you have, over here you would have like a battery, and this would be, say, an airplane or whatever. Or you can even do two batteries. They'll do the same thing. Well, they'll levelize across too if you wire them the right way. The electrons that are here will flow over into those. Because remember, you have atoms that have electrons that are coming up, hitting their outer rings, and then getting passed off to other atoms, like so, and then so on and so forth. Once you kind of create that pathway, they'll start to flow until there's nowhere else to go, and then you just kind of like equalize out. And then they're just waiting for the next, either injection of new electrons or the discharging of electrons to the next thing where there's a potential difference between the two. So that's how voltage works. Now, a lot of this stuff is going to be like new to you, and it's going to be difficult. Ask a lot of questions in class. Ask a lot of questions out on the hangar floor. We're going to have a lot of practical projects to test you on this and help you to kind of grasp and understand what it is that voltage actually is. All right, let's talk about current or amperage. We're going to those two will get used interchangeably. They technically mean slightly different things. Current is just like the flow. Amperage is an actual measurement. And, so you'll start to see amps and so on and so forth. But let's go back to our water bucket level or example. Sorry. So you have your water in this first bucket, and it's going to flow over to here because of the potential difference between the two of them that we just learned with voltage, right? So what is the rate in which the water will go from here to there? All right, that gets determined by this connecting pipe that's right there. The so what is that if the pipe is small, then the difference between these two will put this one is still pushing at the same rate. Like you have all that atmospheric pressure that's pushing down on that water, that's shoving it over into this bucket, right? So the rate in which it flows will depend on the size of the pipe. So if it's a small pipe, we'll say that's 1. But if it's a bigger pipe, we'll say it's 0.5. It's still going to flow the same amount of water. It's just going to do it slower because it doesn't have to flow as fast. If you make sure that the pressure coming down here is the same, like we'll just say it's like 14.7 pounds per square inch, because the atmospheric pressure pushing down on the water, pushing water through this pipe. Well, if it's super tight, it's gonna go like really, really, really fast, because it has to do something with all this pressure. But if it's a really big pipe, well, it's still gonna move the water, but it's gonna move it a lot slower because it's easier to move a larger volume of water at that rate. It's basic math that determines all of this. But that is how amperage works. Whenever you start looking at a electrical conductor, the conductivity of the metal obviously will has a factor, but also the size of the wire makes a big difference. Big wires can conduct a lot of electricity. They can handle a lot of amperage. Small wires can only do so much. If you think about it in terms of, let's say like you have a wire, and you have your electrons that are going from atom to atom. Well, they're like, stacked in here like this, right? They're like standing in line, just like shuffling on like lemmings. Well, if all of a sudden like you start really ratcheting up the power and you start really trying to push through there, they'll just go fast. They just have to keep on going faster. The amperage has to raise up. The faster they go, to move all those electrons through. Well, what ends up happening is that like where it's touching the conductor, it causes friction. Just those atoms just scraping through there, right? Well, the faster they go, the more the friction kicks up. The more the friction kicks up, the more likely you are to have like a fire or the wire melt or so on and so forth. And that's something that we're gonna like get into both with risk management and everything else, and teach you how to know what amperage you're gonna be working with, what amperage is safe, and what are the implications of it if it gets too high. Okay, so now let's talk about the third leg of the triangle before we get to actually Ohm's law, which is a triangle, and talk about resistance. So we talked about voltage. There's the difference in potential flow or potential energy that we're using as our metaphor for water that's in this tank that's going to flow to this tank. And as that flow happens, the rate in which it flows is amperage. So as this starts to flow in and fill up this tank, the speed in which it happens, we will call amperage. Now, resistance. We talked about how like the rate in which it's flowed is affected by the size of the pipe here that connects them. This being 1 and this being 0.5 in terms of speed in which it flows from one tank to the next. Now, resistance is the measurement of the size of that pipe. Amperage is the rate in which the water goes. Resistance is the measurement of the size of the pipe. So this is a higher resistance or a higher ohm, pipe, and this metaphor, and this is a lower resistance. It means that it doesn't necessarily, give as much resistance to the water flowing. The difference is that like the higher the resistance goes, if the potential energy or the voltage stays the same, well, the amperage has to come up because it's like the voltage is staying the same. The resistance comes up. The only way to balance the equation is just with more amperage. If the resistance goes back down, the amperage goes back down. And that is the basics of resistance. Now, we'll get into resistors and the resistance of certain things. If you do like electrical engineering, you'll have to factor in like inside of a circuit board how much internal resistance is to all these different factors, and does that change the voltage enough to change the signal that I'm trying to send through the board. This will also become a factor whenever you start to troubleshoot aircraft. Like on a small Cessna 172, it's like not a big deal to go from a wire from the nose to tail, because you're only talking about like 20 or 30 feet. But when you're talking about like a 777 or a 747 that has to go from, let's say, a 747-400 in the cockpits at the very, very top, let's say if you wanted to go to the tail light, That's a long ways. I mean, it's like several hundred feet, and you have to think about the drop, and then all of the snaking that has to happen in there. That wire, there's no telling how long that is. I'm talking about like hundreds of foot of wire. And so if the resistance of that wire is just a little bit too high, it drops the voltage down there, or amps up the amperage to the point where it could cause damage, it could cause a fire. Or most likely, it won't do the thing that you want it to do. And so understanding those three, the voltage, current, and resistance, and how they relate to each other is super, super crucial. Okay, we're going to give you a real-world look at a metaphor for electricity with our water hose. Now, we're out here at the T hangars, the self-serve. You're going to become intimately familiar with that when we start doing aircraft fueling and so on and so forth. But our water hose represents voltage. There's potential water coming into the world through here. This is like a battery. It's packed. It's ready to share, what it has. And so here we go. Our water hose is flowing, and the rate that it's going at, let's say that's 1. That's the amperage that it's flowing out at. All right. Now, if I increase the resistance, if I put my finger over this, notice that the water speeds up. It actually goes further. It almost like hits the old emergency shutoff over there. And that's because the resistance has increased. Therefore, the flow rate has also increased, because the same volume of water has to pass through a smaller area, and therefore the speed is kicked up. That means that the amperage is higher. So if you look at like kind of a classic example of the way that the electrical laws play against each other, the way those factors play with each other, is with the water hose. Is that the water hose, it represents the voltage, the electrical potential that's there. The flow rate, the water, represents the amperage. And then the resistance is represented in how big the opening is. And that gives you different rates of flow for the water. Okay, all right, here's a look. Now let's take everything that we've learned and let's start applying them and seeing how they relate to each other. What's the relationship between current and resistance, and what's the relationship between voltage and resistance and current, and all the different little principles that we need to really instill in our brains to properly understand the system, because you're going to be called on to troubleshoot these systems. One of the first things that you need to do as a good troubleshooter is just simply understand, how is it supposed to work, and then how is it actually working? What's actually going on? Because troubleshooting is the art of finding the disparity between those two things. This is what it's supposed to do, but this is what it's actually doing. So right now, what we need to do is focus on trying to learn the mathematical relationships and the interplay of all these different electrical forces, so we can understand how things are supposed to work, and then we'll go on from there. Okay. So one more measure that we need to cover before we kind of go on to like a practical metaphor, and then we get into the math side of it, so that way we can all kind of understand. What we want to do is like understand the basics, understand what it looks like, and then we'll start to dive into the real technical side of it. But we want to talk about right now is power. So power is expressed in watts. So if you think about like a 30 watt light bulb that you may put into your house, or a 100 watt light bulb or whatever, that's what it's measuring. So power is equal to the amperage times the voltage. That's basically all boils down to. So your voltage in your house is always the same. It's like 120 volts AC. All right. So then the power then becomes a function of how much amperage do you want to draw, how much power do you want to burn. Like if you wanted to cut your electrical bill back, you could put like really low level lighting all throughout your house. I don't know how much it would actually save, but it would draw less amperage because it takes less power to just emit just a little bit of light. And so there's that. Now this becomes like a big deal in aircraft, because certain circuits are only wired, it can only handle so much amperage. You might have like you know, 400 volts AC going through a jet, but like we only really want like 5 amps going to this you know, one application, or maybe we want 50 amps going over there. Those all scale up and down the level of power that's going through a circuit. So that's power expressed in watts. Okay, the most fundamental of all electrical laws is Ohm's law. Now, Ohm's law states that amperage can be found by taking the voltage divided by the resistance, or you'd say amps by volts over ohms. All right. It's frequently expressed in terms of a triangle to kind of help you make quick math of the algebraic way of rearranging all of this, where volts is on top, amps is over here on the side, multiplied by ohms. Now, if you wanted to find the volts, well, you would just simply multiply the amps and the ohms, so you should get the volts, all right? If you wanted to find the amperage, well, you would take the volts divided by the ohms in the circuit, and you would have the amperage. Same thing if you wanted to find the resistance in the circuit, just take the volts divided by the amps, and you should get the ohms. Either way, if you know two, you know the other one. Now, this becomes a lot easier as you start to kind of learn the system that you work, because this is typically going to be like 24 volts DC, or say 400 volts AC, VAC, or you know, whatever. Like there's also 28 volt systems, so you'll generally kind of know what this is supposed to be at. Now, you generally won't know what the resistance is at, but you'll have a good idea where the amperage is supposed to be at. Now, whenever you start to troubleshoot, you can start checking power, and you can start saying like, hey, look, is the voltage right? Because if the voltage is low, something is off. We're either not producing enough power, or there's a lot more resistance. Most of the time, it's going to be there's something going out, and the resistance is starting to skyrocket and dropping the voltage, or changing your amperage. But either way, this is kind of like a fundamental one where you'll use it, but you won't necessarily math it out on paper. It's more like you need to do a lot of math problems to understand the relationship, so that way whenever you're starting to look at a problem, you can say like, okay, what do I know? And then what blanks can I fill in? Or where do I need to start kind of sleuthing to try to figure out where the problem is at? And we'll get into this a little bit more, but for right now, we're gonna just do a couple of practice problems on Ohm's law and just kind of work through it. Another fun one called, if I can spell his name right, that's Kirchoff's law, which is, it's spelled Kirchoff. There you go, Kirchoff's law. All Kirchoff's law basically says is that like whatever goes in is equal to that whatever goes out. All right. Now, mathematically, they'll try to express this by saying that like it's always set to 0. So like, you know, your I1 plus I2 plus I3, they all set to 0. So all these numbers have to set to 0 in some way, shape, form, or fashion. The easiest way for me to understand it is to draw a circuit. Let's say there's a light bulb on this circuit. All right. And there's a battery over here. So that's our battery. This is our light. Not using like a proper symbology here, but that's for a reason, to try to make it super easy, super simple to follow. So we got our battery and our light. Now, what they'll say is like, hey, look, you know, another way to say this is that the rise is equal to the drop. Okay. The reason being is that like, let's say we have our circuit here, and our current's going to flow this way. And we got 10 volts it's just raised up. We're super happy. We're going to work, like just having a grand old time. And boom, we hit the light. Now it's time for that power to do its work, and it's going to cost 10 volts. So what's going to come out right here? If you had 10 volts coming in, the cost 10 volts should 0 volts coming out. All right, and then comes back here, and then you have the rise, comes back up to 10 volts, comes back around to the voltage drop over here. All right, now that may seem backwards to you because, in theory, like you wouldn't want to just go and lick this wire or whatever else because it's still probably got 10 volts in it, but that's Kirchoff's law. All right, so why does this matter? All right, I'll tell you why. Let's have that same circuit. Got our battery. But this time we're gonna have 2 lights, all right? Now let's say like this one takes 5 volts out of the system. This one takes 5 volts out of the system. If I'm trying to troubleshoot like why these lights aren't dimming properly or why this one is out, what I want to do is come over and take my meter and check right here. All right, if it's anything less, if we know we're putting 10 volts DC in and it's going around, then what should it be right here? Should be still have 10 volts DC. If it's anything less than that, then I know that there's extra resistance in this light. If it's anything more than that, then I know that this light bulb is probably not doing what it's supposed to do, and we need to change the light. Or maybe the connector here or here is corroded or broken or somehow not right. If everything's right, and then I should be able to come back here and say like, okay, well, the same problems are happening over here if this light's dim. But that's how you would employ it. Now, this is a kind of like a really high-level overview of Kirchoff's law and employing voltage drop analysis in a circuit. And we're going to practice with this as we get going to where there's about a dozen ways that you can start troubleshooting. And that's one of the cool things about electrical troubleshooting is that there's no one right way. There's 1,000 ways to go about doing it. You could do the same thing by taking the battery out and shooting this wire run and seeing if you have a super duper high resistance and like 7 or 8 ohms. We're like, okay, well, we got a problem down here. Then we start looking for all the different possible places that it can be. Where this becomes useful is that if you're trying to turn a plane that's just landed and you need to get it kicked back out, but they're saying, hey, look, we're having this problem, or you have an intermittent fault, this is a good way to start kind of running those problems down. So you have relay contacts that get worn out over time because they're constantly touching, and as they go to touch they arc and then pin each other, or they have corroded places, especially whenever you're talking about outside of the plane or where there's a really high level of environmental factors like the landing or the landing gears the wheel well. These are places that you can employ Kirchoff's law in a pinch to really get things going. You need to be safe, and there's ways to do that, but this is just one that you should be aware of. And we're going to do some more problems to kind of help play with that and kind of get that in our brains. Okay, let's talk about Watt's law. Watt's law. Watt's law is really easy. Power is equal to amps times voltage, which is actually E. All right, so you say power is equal to amperage times, that's not how you spell amperage times volts. Okay, so if you wanted to start troubleshooting with this or understand it, you could take your multimeter, hook it up to the circuit, and say what's the watts? So this is always expressed in watts. Now you should know about what that should be. Generally speaking, the maintenance manual or engineering will tell you that, hey, look, we know it's a 24 volt system. We know it's supposed to be going at 100 amps. So therefore we should have a 2400 watt, output over here. If it's anything less than that, then we have a problem with one of these two places. If you know that your voltage is correct, well then you have an amperage problem. That's for whatever reason you're not producing enough amps. Or let's say this is super duper high. Maybe your amperage is way higher because something's burning out or something's not connected right, and that could cause a fire. But that's Watt's law. So let's work a couple of problems with that. Faraday's law basically states that if you have lines of flux and you have a conductor that runs through that lines of flux, we'll label this lines of flux, and then a conductor, then electrons, as they travel through this line of flux and they encounter that conductor, they'll also turn and go with the conductor and actually start piping electrons through there. Now, that sounds like complicated, but it's really not too bad. And it's really important when it comes to motors, and as well as other things. So like motors, for example, we'll learn all the parts and pieces of it here in a minute, so we don't want to get too jargon heavy. But let's say you have like a apparatus that looks something like that, and you have two magnets on either side. Okay? So you have a magnet here and a magnet there. Now we know from earlier that this magnet is going to have lines of flux like this that are going around, and they're just pumping electrons through there, and they're circulating around, and this thing is spinning. As it spins, it starts grabbing electrons from these lines of flux, and it starts piping it down this way like so. All right, that is how a basic motor works, or in this case it's a permanent magnet alternator is what we've basically lined out right there. But electric motor, either way, it grabs electrons from these magnets and then pipes them down a conductor, and then they go off into the netherworld to be used or wherever else. Now, that's one way that Faraday's law actually gets employed. But essentially, you're going to use this troubleshooting for the rest of your time. I remember, I'll show you all pictures. Matter of fact, I'll put pictures up of the thing that we built to try to figure this out. But essentially, we were working on a KC-46, and so like I said, that's the nose of the airplane. You have the cockpit up here, and back here was so you had like a refueling station for mission systems, and then there was a bunk, all right? Now, right here in the bunk, there was a place for you to lay down and go to sleep. There was a headset, and that headset was connected to all these other stations. Well, all the other headsets were clean. They had nice, clean audio, no problem. But when you got back here, it was like screeching in your ear, and we couldn't figure out why. We troubleshot the wires, did all kinds of stuff, and what we ended up having to do is taking a CNC, the Cal says move, you pull the string on the CNC, went from a battery to the CNC. So we'll write this out: battery, CNC, to an amplifier, and then back here. And what that did was that it basically, the amp projected out a radio signal, and we walked up and down the sides walls of the airplane until we got right here, right beside. So here's the door. Right here, there was a junction that wasn't grounded, and it was picking up all of this electromagnetic frequency, because there's a lot of electricity piping down the walls of these airplanes, especially like a military airplane like that. And that CNC was picking up that junction was picking up all that EMF, and it was just dumping it in the crew rest bunk audio. And we were able to have a guy sitting right there, pull the CNC, and you could hear the Cal says moo in the headphones back here. But that all came down to a principle of Faraday's law, and that's a way that you can use Faraday's law to troubleshoot. And so, like, once again, there was no math done, there was no like super duper reasoning. It was just we realized kind of what was happening, and we used Faraday's law to essentially employ it so that way we could troubleshoot it. And that's what I want to get you guys to start understanding. It's not we're going to have you do math because you have to pass the test and you need to really kind of learn the relationship with things. But it's not necessarily judging your math; it's judging your reasoning. Can you take these things and put them to work for reasoning? But yeah, so let's talk about another law. Okay, so let's talk about Lenz's law. So Lenz's law, that's spelled Lenz, like so, says that if you have a coil, like so, you attach that to a meter, okay? And we take our magnet, so this is our north end and our south end, and we slide that magnet into this. Now, if you remember earlier, our left hand rules with the magnets says that, hey, look, if I grab it with my left hand, the lines of flux are going that way, right? Well, as I move it in here and it starts to induce a charge from Faraday's law, then we know that this will then become the north end of the coil, and this will become the south end, because Lenz says that anytime that a charge is induced from a magnet, we use our right hand. It goes the opposite way. So that we would grab this and the lines of flux would be going that way, whereas this one would be going the other way. All right? They would be opposing each other. And then if we were to slide the magnet back out, then it would be totally different. It would start to, this would be the north end, and that would be the south end, and it would try to grab. Now, this may seem super confusing, and you're not gonna have to do any math that's attached to this. You just have to know that as the magnet slides in and out, the current that's being induced goes backwards and forwards. It goes one way, and then it turns around and flips the other way, or reverses the other way. And that becomes the basis for alternating current, which we haven't talked about yet, and we will. But remember Lenz's law. Okay, so this is the last one of the kind of the laws. It's called the right-hand motor rule. Essentially, the right-hand motor rule is going to give us the foundation for electric motors and generators and so on and so forth that we're going to study here in just a little bit. What the right-hand motor rule says is that, like, you can take your right hand, you point keep your hand flat, you point your thumb in the way that the current is going, and then your fingers to the south end of the magnet that the wire that the wire would be running through, and then toward the direction of your palm is the way that the magnet will push against that wire. Because remember, the magnet has lines of flux. So if you think like you have a magnet, all right, and let's say that south is up here and the north is down here, and we have a wire that's running through there, okay? And we put a charge on this wire. We're going to, the charge is coming at us, okay? It's coming towards the camera. We put our hand flat, the thumb is pointing towards you, our fingers are pointed to the south. That means when we run the current through there, the wire will go this way. It'll push out that way, because you have two opposing forces that are pushing up against each other. You have a Han and Han, not a Han and Leia scenario. This now for troubleshooting and stuff like that, you probably won't ever actually use this. Well, you will use it, or maybe you would in certain scenarios. Where you will use it is trying to understand, why do electric motors work the way that electric motors work. And as you start to kind of like wrap your brain around this, that like this is emitting, like, let's just do different colors. That this wire is emitting lines of flux, and the magnet is also emitting, like lines of flux that go out like there. I guess it would be a little bit different, but you get the idea. Whenever the current gets piped through there, remember that if you double the current, you double the electromagnetic field that is being produced. Well, now we double up on the current. It has nowhere to go other than to push up against each other. And the right-hand motor rule tells us which direction is it going to go. Is it going to go towards the magnet? No, it'll go away from the magnet. It'll push out, because we can put our hand right there, point our flat hand towards the south, and we know that our palm indicates the direction in which the wire will travel. So that is the right-hand motor rule.